Okay, so my today's talk will be probably short. I just wanted to finish discussing homotopic completeness and co-completeness of model categories. So the key idea was to discuss some sort of subcategories of virtually cofibrant and fibrant objects that will allow us to, well, they already allowed us to construct approximations to limit and co-limit functors using retractions to these subcategories. So the general topic remains the same: homotopic completeness and co-completeness of model categories. And the main topic of today's discussion will be virtually fibrant and cofibrant objects. In categories MD or D, some small. So virtually fibrant and cofibrant diagrams. So as was promised, the idea is to find some sort of subcategory of virtually cofibrant diagrams and virtually fibrant diagrams, such that the subcategory of virtually cofibrant diagrams is a deformational retract, a left deformational retract of MD, and subcategory of virtually fibrant diagrams is a right deformational retract of MD. So first we start off with the notion of restricted delta D and delta of D diagrams. And so assume that we have a model category M. We have a small category D, and we have some diagram X. Diagram over simplex category of simplices in D, or the opposite category of simplices in D. And we say that X is restricted if for any map in the category of simplices in D, or in the opposite category of simplices in D, for which the associated functor between chain categories M1 and M2 sends N1 to N2, or respectively 0 to 0, the map XH in M is a weak equivalence. And we denote subcategory of such restricted diagrams by this subscript res, and similarly for the opposite category. So we have the following proposition that justifies the existence of this notion. Let M be a model category as usual, and let D be a small category. Then, first of all, the adjunction involving projection functors, colimits of projection functors, is a deformable adjunction. So we have junction like this. And respectively, we have an adjunction involving the initial functor, the initial projection functor. So this is a deformable adjunction. Moreover, this adjunction satisfies the Coulomb condition, which we formulated, and is a condition when certain junction of certain deformable adjunction, or more in a stricter sense, just Coulomb adjunction, is a Coulomb equivalence, or an equivalence on homotopical category, on homotopic categories, if we're talking just about any deformable adjunction. So it satisfies the Coulomb condition, and that means that for every radicofibrant, respectively, radiofibrant object X in the category of restricted diagrams, or in the opposite category, category of restricted diagrams from the opposite category. And every object Y, which is just a diagram shape D in M, a map from X to T upper star of Y, which is a map of restricted diagrams. Or if we're talking about limits, then it's a map from EI upper star Y to X. So this map is a really with equivalence if and only if it's joined map in category of diagrams of one form or another. Is an object-wise weak equivalence. And hence, as we explained when we discussed condition for deformable adjunctions, these functors are inverse homotopical equivalences of homotopical categories. We'll prove this proposition later. And this result suggests the desired notion of virtually cofibrant and fibrant diagrams. So assume that we have a model category. We have a small category. And assume that we have a diagram of shape D in M. And we say that it is virtually cofibrant if there exists a really cofibrant object X, where X belongs to the category of restricted diagrams, such that Y is isomorphic to the value of the colimit functor with respect to terminal projection of this on this radiocofibrant object. And similarly, if Y is a diagram, we call it virtually fibrant if there exists a really fibrant object X, also a restricted diagram, such that Y can be represented as a limit of the initial projection functor on this X. Finally, we assemble all these objects into twofold subcategories. So we have virtually cofibrant objects, and we have virtually fibrant objects. They span a subcategory. And this gives us desired subcategory. So now we can finally prove the proposition that give us various properties of these subcategories. The main one being that they're deformational retracts of categories of diagrams. So let me briefly recall this deformability result, as we call it then. So the claim is that, first of all, for any model category M, small category D, there are full subcategories such that first D is a left deformational retract of MD and subcategory of virtually fibrant objects is a right deformational retract of MD. The second point is that if we have a equivalent junction, then the induced junction, then the induced functor on the diagram categories, so like this, sends object-wise with equivalences in subcategory of virtually cofibrant objects, object-wise with equivalences in subcategory of virtually cofibrant objects in ND. And analogously, functor GD sends object-wise with equivalences in subcategory of virtually fibrant objects to object-wise with equivalences in subcategory of virtually fibrant objects. And the final point is that if we have a model category and U is some functor between small categories, then the functor called MU, which goes from category of diagrams of shape A category of diagrams of shape B. Since object-wise weak equivalences in the subcategory of virtually cofibrant objects, two object-wise weak equivalences in subcategory of diagrams with cofibrant objects. And of course, the same thing holds for the limit functor, which sends object-wise weak equivalences in subcategory of virtually fibrant objects. So object-wise weak equivalences in subcategory of diagrams with fibrant objects. Okay, and now we can prove the statement, which afforded us all these results about existence of homotopical limits, etc. So to prove the first point, one notes that in view of the proposition about restricted diagrams, for every left deformation RS, for every left deformation RS from this into the subcategory of cofibrant, rigid cofibrant objects, the pair consisting of the functor equilibrium of terminal projection R P upper star T from MD to MD, and the natural transformation that looks like this. So this natural transformation associates to each object of the diagram category. the adjunct of weak equivalence given by the following. So just use this information to give us these weak equivalences. So this pair consisting of this functor and this natural transformation is in fact a left deformation of MD into into subcategory of virtual equifibrant diagrams. So we've constructed a desired deformation. The second point follows from the fact that for every rigid category B, equivalent adjunction FG induces equivalent adjunction between categories of diagrams. And it remains to observe that F delta D sends restricted diagrams to restricted diagrams. So the second point, which asserted that if we have equivalent junction, then objectivize weak equivalences in subcategory of virtually equifibrant objects are sent to objectivize weak equivalences in subcategories of virtually equifibrant objects. Since restricted diagrams are preserved, it means that virtually equifibrant objects are also preserved, and weak equivalences are sent to weak equivalences between them because we have equivalent adjunction. Oh, strictly speaking, of course, we only know that weak equivalences between rigid equifibrant objects are sent to weak equivalences between rigid equifibrant objects, but it is sufficient because definition virtually equifibrant objects are defined as colimits of rigid equifibrant ones under projection. So we see that weak equivalences are sent. It finally remains to prove the third point of this proposition, namely that if we have a model category and functor between small categories, then colimit functor between diagram categories, sends object-wise weak equivalences in virtually cofibrant objects to object-wise weak equivalences in category of diagrams with cofibrant objects. Okay, so to verify this, assume that x1, x2 are two video cofibrant diagrams in the category of restricted diagrams. And assume that we have an object-wise with equivalence given by certain f, which goes from the colimit of x1 to the colimit of x2 is object-wise equivalence in category of diagrams of shape E. Then we have an induced map which goes between two objects to which we applied the functor column U. And now it is a map in diagrams of shape B. And the induced map is an object-wise weak equivalence between object-wise cofibrant diagrams. This is what we need to show. So we start showing it by constructing the following commutative diagram. So first of all, we have a trivial cofibration. Followed by trivial fibration. Which goes into P upper star T of Et, colimit of x2. And here, similarly, we have just some weak equivalence, just some weak equivalence that goes from Et upper star, colim Et of x1. This is also equivalence because we have such a natural transformation, and which is such natural equivalence. And we have PT upper star F, which is also equivalence between these two. So obviously the induced diagram functor preserves object-wise weak equivalences, which is since f is 1, it is preserved. And also here we have a map from X2 and another weak equivalence, which comes from the existence of a natural equivalence, the composition of the upper star T equaling PT. So on the vertical maps, as I said, are the unit maps, so the unit of the adjunction between the induced diagram functor and the limit. Yeah. So maps A and B are factorization of the weak equivalence the upper star TF and the T X1 into trivial radical vibration followed by trivial radical vibration. And finally, the map E is obtained by lifting the T X2 along B. Then using the adjunction, we get a commutative diagram in MA. Commutative diagram looks like this. So yeah, we just got rid of ET upper star and replaced it with the column T by a junction. Now we can apply the functor quantum Q to this diagram, and we obtain a diagram in MB, which looks absolutely similar. Okay. So the two top maps, these things are object-wise equivalences between object-wise cofibrant objects, which in turn implies that the bottom map is also an object-wise equivalence between object-wise cofibrant objects. Now, so we've proven the deformability result. Now we want to prove the proposition about restricted diagrams. Okay, so assume that we have an object T in category D, and let T minus 1 D denote the subcategory in the simplex category. The subcategory such that objects are functors from this chain categories to D for all non-negative n, such that En is equal to D, which means that the projection functor maps this object to D. And as maps between such objects, we consider the functors from n1 to n2 such that, of course, they form a commutative triangle, and En1 is equal to to n2. So this is sort of is the fiber configuration delta D to D. So what are the properties of this partially defined category? Well, this category has an initial object which is the functor ed from the zero simplex, if you will, to category D, such that ed of 0 is equal to the object D, which is the only possibility really. And moreover, it is a witty category where the increasing and decreasing subcategories are defined just as intersections of the respective subcategories with this preimage of D. And moreover, we can see that the decreasing subcategory is a disjoint union of categories with terminal object. That's the first point. The second point is that for every witty cofibrant diagram X in M delta D, the diagram I upper star X, which belongs to the category of diagrams indexed by this preimage category in M, induced by the inclusion functor from this fiber into the whole simplex category of simplices. So this diagram is also witty cofibrant. In view of the fact that dn from n-1 to n denotes a functor such that dni is equal to I for I the set of non-negative numbers from 0 to n. Then for every object E, which is a functor from n to d, and such that it belongs to the fiber of the object d, and n should be greater than 0. The commutative diagram has the property Lx E dn star x x E dn x E x E. So it has the property that the square on the left is a push-out square, and the map Lx EDN to x EDN, and the map XLE to XE are cofibrations and therefore the map L I upper star x E to I upper star x E is also cofibration. Therefore, for each object D, category D, the diagram Y in MT and radio cofibrant X which is also a restricted diagram, and the map from X to E upper star T Y, which is a map in category of restricted diagrams over category of simplicity. We have a commutative. We have an induced commutative diagram. This diagram, oh, let me think how to plot it. Oh, let me try to use a smaller pen first. Okay, so we start from here. We go to so we can consider such a diagram. Where J from this comma category is just a forgetful functor. And this maps these maps here, A1 and A2, are isomorphisms because because of the properties of the connected functor. It doesn't matter if we take colimit with respect to ET or with respect to this over category if we then compose with the forgetful functor. So these maps here are induced by the functor K. the following form, which sends an object E in this image category to the object E1D in this over category, and are isomorphisms because because functor K is right cofinal. Let me explain what that means. This means that for any object in this category, the category EK is not empty, and every not empty and connected. Maybe, yeah. So non-empty and connected. Any two objects can be connected by zigzag lines. C1 and C2, let me write them down. Well, it's pretty clear what they should be. C1 and C2 are the restrictions to ED of the respective limiting components. And this implies that C1 is a weak equivalence and C2 is the plane isomorph. This follows from yeah. So this flows from the corollary which we stated about media categories with fibrant and cofibrant constants. And finally, we can deduce that the composition C2 minus 1, 2 minus 1, E2, which goes from column T, T upper star Y to YD to YD is the restriction to D the counit junction PT from restricted diagrams to just diagrams. And finally, we see that the composition of this map with the map from column PT XD to column PT upper star YD is the restriction to D the adjunct given map X to PT upper star Y. And from this, the statement readily follows. Okay, I think I want to finish today. As promised, the talk was rather short, but I just wanted to sort of tie up all the loose ends. And maybe next time someone else will talk, or maybe I will give somewhat introductory talks into homotopical categories and stuff like this. So more formal discussion of homotopical categories. As before, we used them a lot, but we did not really talk about them in particular. Okay, thank you for coming, David, and hope to see you, and hopefully somebody else this Friday.